I'm Dr. Bill Coxe, here to interview Dr. Sidney Goldring. Sid, I've known you for many years, but I don't know a lot about some of your life. Can you tell us something about your early life and comment upon your family and their influence upon your career?
Well, as I think you probably do know, I was born in Poland and came to this country when I was 3 months old with my parents and brother. And they came here because higher education was very difficult to come by in Poland at that time. And they put a great deal of emphasis on educating their children. My brother, who always satisfied their expectations, always provided big shoes which I never was able to fill. But ultimately, his efforts were successful in giving me some direction, and I decided that I wanted to go into medicine at a relatively early time in my career. As you know, he's a pediatrician, cardiologist, now retired. My days in grade school and high school were nothing that we'd want to review right now. They were certainly just average. And I think I finally came to a decision to pursue a career and settle down in business when I entered Washington University, when I entered college.
After entering the undergraduate school, you then made a decision to enter medicine. Was your brother a large influence in that, or others?
To a large extent, and the friends and people that I was thrown together with, all those things influenced me to go into medicine. I never really seriously considered, once I'd made up my mind to pursue a career, I never really seriously considered any other profession very seriously.
Well, you were in medical school during the middle of World War II, and at Washington University, and as all medical schools, the faculty was much smaller than it is nowadays. The atmosphere was somewhat more intimate. And did you have any comparisons to make about then and now with reference to the school then and as it is now, or other schools, and the members of that faculty that influenced you so much?
Well, I don't know that I can make very much out of a comparison, except I guess the biggest change that I saw as time went by is that one always knew all the faculty, and faculty members could always park on the parking lot across the street from the school. And now faculty have to compete for parking places with the drug salesman and everyone else. So things have gotten bigger. Whether they become better, I don't know. I was fortunate in that we had a very unique faculty at Washington University when I was a student. There was Joseph Erlanger, who was the head of the Department of Physiology, who had just won the Nobel Prize for his work with the compound action potential of the peripheral nerve. There was Carl Corey and Gertie Corey, also Nobel Prize laureates. One was the head of biochemistry and the other pharmacology, and they won the Nobel Prize for discovering the metabolism of glucose, the cycle. There was Hershey in the Department of Bacteriology, also Nobel Prize laureate. I must say they were all famous and awe-inspiring, but I wouldn't give them an A as teachers. They left something to be desired. They did very well on a one-to-one basis, but not to a classroom.
Well, excuse me, in the course of your, towards the end of your medical school career, one of the people I know, the young professor of medicine at Washington University, Barry Wood, was a tremendous influence on many people there, and he, I think, was an initial influence in your career in research.
Right. Barry Wood was made professor of medicine at Washington University and head of the Department of Medicine when he was 32 years old. He had already had a distinguished career in athletics. He was an All-American quarterback. He played on the Davis Cup tennis team. Tall, handsome man. In fact, some of the research he did in the locker room of the football team, and that is that he demonstrated that white count goes up when you exercise, and so it gives you an idea what kind of a resourceful individual this man was. And that's right, he is the one that started me, or got me interested in research. We were on ward rounds one day, our particular group in the clerkship on medicine, and we had been presented with a case of meningitis, and who had a low spinal fluid sugar, and I said, what causes the sugar to be reduced? And he thought for a while, and he says, we really don't know. It could be the bacteria, and he says that might not be a bad subject to go to work on and try to find out. So I took him at his word, and I went to see him, and one thing led to another, and I wound up with a large laboratory and some mice with which to do the experiment. Well, that involved doing cisternal punctures in mice and simultaneously drawing a blood sample. And after spending a month or so on that and not being very successful, I was ready to quit. And John Smith, who was down the hall, a cardiologist, was leaving for Italy, and he had half a dozen dogs that he willed to me, and we were able finally to make it work. And to make a long story short, the work did result in a publication, and I was inspired by that, and I think that really is what opened the doors for me and introduced me to a major interest in research.
But after that, your interest was in neuroscience.
Well,
and you came into contact with
right.
a number of other people.
Yes, I'll tell you about how I came to become a neurosurgeon. When I graduated from medical school, I was sure that I wanted to pursue an academic career. I had visions of having a small ward, maybe of 10 or a dozen patients with a related medical condition, with a laboratory nearby in which I could both minister to the sick and at the same time carry out research that might improve their situation. I was pretty well set on that. And I thought that the thing I ought to do would be to perhaps spend some time in the laboratory doing research, learning what it's all about. I went to see Barry Wood for a job, and at that time I hadn't focused on really on neurology or neurosurgery. Well, he didn't have a position for me, and he said, are there any aspects of medicine that interest you more than another? And I said, yes, I think it's the nervous system, but I just don't know, I can't be more specific than that. And he said, well, I would suggest that you go over and see Jim O'Leary. And James L. O'Leary, as you know, was late James O'Leary was the head of the Department of Neurology at Washington University and influenced a good many neurologists and neurosurgeons in their careers, in the pursuit of their careers as clinician investigators. When I went to see O'Leary, he told me that I could have a job, I could work with him. He needed some money for a stipend, and he sent me off to be interviewed by Sam Clark, who was one of the people who sat on the Scientific Advisory Committee of the National Research Council. And that was here in Nashville, in fact. It was at Vanderbilt. And I had the interview, but I didn't get the grant. And Dr. O'Leary scraped up what in those times was considered not too bad a salary. I had was $1,200 for that year, and I went to work for him. And with that started a collaboration, first as pupil and teacher, and later as collaborators in research, which endured over, I'd say about a 20 to 25-year period.
The initial work that you did with him or collaborated with him had to do with, I think, your interest then was in the cerebral cortex and perhaps seizure.
Well, I'll tell you how that came.
DC potentials, of course, constituted an enormous amount of your work in the study of that phenomenon.
Right. O'Leary had the idea that there were DC fields around us that influenced neural activity and fields about which we were entirely, unaware. And my job was to find evidence for those fields and demonstrate their influence on cortical excitability. I met with hard times in trying to demonstrate that. In fact, I couldn't demonstrate it. But what I was able to demonstrate was that DC changes, that is the difference are a voltage gradient between the surface of the brain and some inert point like the neck muscles, that changes in that DC potential occurred whenever there were perturbations of the nervous system. If an animal was made anoxic, there would be a DC change. If an animal had a seizure, there would be a DC change. If you activated the cortex by stimulating the peripheral sensory mechanisms, there would be a DC change. So they were a consequence of perturbations, but we didn't find any fields out there that would, demonstrate whether what you did or what the animal did. And of course, today, some 20 to 30 years later, such fields have been demonstrated for marine life and also for migratory birds. And with marine life, where the fields can influence their behavior as escape from predators, or relocating themselves, or finding food. In any event, we did demonstrate the DC changes. And what we didn't know is what did those DC changes reflect. And at the risk of belaboring it, I think I will tell you just another brief bit of information related to that period of research. In about 1956, a man by the name of Charles Phillips from Oxford, was able to impale a single neuron with a cortical neuron with a microelectrode and record the membrane changes of that neuron. And so this was the first time that it became possible to study the EEG, or from the surface of the brain, simultaneously while one was looking at a single cell, and see to what extent the EEG mimicked the behavior of that cell, or what other insights one might gather from that type of observation. And when he was poking around trying to get into those cells to make his observations, he would encounter one cell in which there was a change in its membrane potential upon impaling that cell, but beyond that it did nothing. Whereas if he impaled a neuron, there would be periodic activity, so-called synaptic potentials, that would be recorded. And its action potentials would be recorded. And he called these quiet cells idle cells because he didn't know what they did. And a number of us throughout the country became interested in looking at at a single cell and the EEG simultaneously, and see what we could learn about seizure mechanisms as the behavior of the brain went from its interictal state to a frank seizure, and gather information by comparison between the activity of the entire population and a single cell. And what we were aiming for were single neurons. But we too would impale these idle cells like everybody else. And one day, I might add that a man named Aichi Sugaya from Japan, who came to this country to spend 2 years with me. By the way, he was recommended to me by Paul Busey, a good friend of yours. We were doing an experiment one day in which we were using metrazole injection as an experimental model for seizure discharge. And he had impaled one of these idle cells and hadn't come out of it too quickly, which was usually what we did because they were of no interest. And while that electrode was in that idle cell, the seizure activity developed in the record as a result of the metrazole, as recorded by the EEG. And every time there was a blip on the EEG, there was a depolarization in the idle cell. And that was the first time anyone had demonstrated that these cells did something besides just sit there idly. And then the big question is, what were they? Were they short axon neurons that behaved differently than the other cells, or could they be glia? And so for a long time they were either called idle cells or presumed glial cells. And people like Vincent Castellucci and Bruce Ransom. Castellucci, who's now a well-known physiologist and our neurobiologist, and Bruce Ransom, who's associate professor of neurology at Yale. And during the period that they worked with me, one of our main efforts was to be able to find some kind of dye or marker that we could inject into these cells when the electrode was intracellular, to see if we could mark it, see if we could demonstrate its morphology. And we, as well as others, didn't have too much luck with that. And then one day I happened to be visiting my son Jim up at Chapel Hill, where he was doing a postdoc with Stan Cater. He says had I heard of this dye that Lucifer yellow, when injected into a neuron, and showed the entire cell, its cell body and all of its fibers, the dendrites and the axon. And I said, no, I didn't. And he told me about how wonderful it was from what he had seen. And I wrote to the man who had synthesized this dye, and he was kind enough to send me a sample of it. And so we went to work trying to mark these cells, and we did mark them with Lucifer yellow, but we weren't definitive as they were with neurons. And then, skipping a bit, horseradish peroxidase was used, an enzyme also that can be injected as a marker, and it displayed the cell as if it were a silver impregnation. We could see the glial cell body, its extensions, its fibers, the end feet on blood vessels, and so we had established that yes, these were glial cells, and they contributed to the surface record of the EEG because they would become depolarized every time a neuron would become active and secrete potassium. So that was a story related to our venture into, you might say, glial physiology, and which resulted from first studying the DC potentials. And during that time, our main interest was focused on the experimental models of epilepsy.
Well, the development of this whole area in terms of your clinical as well as scientific interest, though, is continued to the present. And do you wish to tie in that older day with the main emphasis of your work as it's evolved?
Right. There's another what I consider important in my interests, or in developing the interest in epilepsy, and that had to do with the advent of the computer into use in the life sciences. And I might also add that what I forgot to mention, that another very important individual in shaping my research career was George Bishop, who was at the university at that time. He's been dead a good many years now. But Bishop was one of the pioneers along with Erlanger and Gasser, in deciphering the various components of the compound nerve action potential. His other contribution was made in the 1930s when he demonstrated for the first time in modern neurophysiology, electrophysiology, an evoked response in the visual cortex. He stimulated the optic nerve and demonstrated a response in the visual cortex that had a very characteristic configuration. Prior to that time, that had never been known except for an observation in the last century when a man named Caton, a physiologist, would move the whiskers of a rabbit, and with a galvanometer placed on the brain showed that every time he moved the whisker, why, there would be a negative variation. So Bishop, by the way, and was in the Department of Neurology, even though he was a neurophysiologist in those days. And I don't want to get into that because that's a story unto itself. But my contact with Bishop was such that a good many of the studies we did were on evoked potentials, how they were modified by anesthesias, seizures, anoxia, and so on. Well, in the early 60s, about 1962, NIH made available 24 computers, which were dubbed Link computers, standing for Link Instrument Computer, which could be used like any ordinary measuring device, like an oscilloscope, in the sense that if you had use for it, you'd wheel it out and use it, and if you didn't, you could push it back in the corner until there was a time that you could. That was unheard of in those days because computers were large computational instruments, usually occupied a large room, and were used as a multi-user instrument. People had some calculation to do why they would bring it to the computer. The concept of the Link computer, which was a very small instrument by the standards in those days, was something that you could actually wheel around. and it was specially designed for the purpose of being applied to biology. And so NIH made available 24 computers like that, and the scientific community competed for them with appropriate application. And O'Leary and I submitted an application, and we were awarded a Link computer. And I think the only reason that they awarded us the computer, we were the only clinicians, and they figured if we could make use of it, that anybody could. And one of the conditions for getting the computer was that one of the investigators had to go to Cambridge and learn how to use it and take part in its final assembly. And in those days, I must tell you that when somebody said program, I didn't think of a computer. I thought of the opera, see, or something of that sort. And I had no idea what it was all about. Well, anyway, I went off to Cambridge, and this course lasted a month. And I'd say that it matched up pretty well with any month that I had ever spent with Henry Schwartz when I was in training in neurosurgery, in terms of the intensity of the work and the caliber of the instruction that we got from that crew, who was under the direction of Wes Clark. Wes Clark, by the way, was a genius. He did not have a higher degree. In fact, I'm not sure he had a bachelor degree, but is truly recognized as one of the pioneers in making the computer available for its special purposes. Two of the conditions, besides going there and taking part in its final assembly, one of the conditions was that before you left, you had to say what you were going to do with it and write the program, at least the initial program, but would permit you to do it. And there's a process known as averaging, which I think you're aware of, which has to do with evoked responses, and it separates the response from the rest of the noise created by the spontaneous brain waves. And by stimulating repeatedly, the random waves disappear, and the response, which has a fixed latency and configuration, adds up and exposes a clear signal above the noise. And so I wrote a program for averaging evoked responses from the brain, and the purpose was that O'Leary and I felt we were in an ideal situation to carry out studies of sensory input into the human brain, which could be done during operations for epilepsy. And so when the computer was shipped to St. Louis, we went to work on that particular project. And I should tell you that computer occupied space with, I guess, our two chairs and this table, but part of it was about 6 feet high. It had a memory of 2K, and its response time to instruction was, I'd say, 20 times slower than any little digital watch that you get now. But that cost $45,000, and now you can, as you know, you can buy yourself a watch with 1,000 times the memory, and which acts much faster, and the price, as you know, has gone down.
You're still using that computer?
Well, the interesting thing, we are, and Wes Clark was recently in St. Louis, and I demonstrated that to him, that this was the only one that isn't in the Smithsonian right now and is still being used 25 years later. The only problem I have with that, and why I don't usually mention it, and of course you did, is that I'm not sure that that's a sign of lack of progress. But we have some other computers that are more up to date, cost less, and do more. In any event, we went to work and studied sensory input, specifically the somatosensory stimulation, and to see what the distribution of the responses were in the brain. And what we found under our conditions of recording was that the only place where we could record a response was in the somatosensory area, and to a lesser extent in the motor cortex. That was variable. And we never saw responses from association cortex. Now what that meant, why that was important to us, is that here was an alternative way to get functional localization in the brain, which is so terribly important in operations for epilepsy, because you need to identify the areas that control movement and sensation and language in order to be able to remove the epileptogenic tissue. You don't have the nice boundaries you have like when you have a tumor, where you can just focus on the tumor. Usually when you operate on patients with epilepsy, the brain looks normal, just like, there's no sign of pathology, and the only way you can find that the lesion is electrophysiologically. And ordinarily what one does in epilepsy surgery is patients are operated while they're awake under local anesthesia, and the brain is stimulated to produce movement or sensation, and of course that requires an awake cooperative adult to be able to withstand all that. It also meant that children were denied surgery if their brain did not have gross pathology, and it meant that some adults couldn't undergo surgery. So that venture with the computer really is what laid the groundwork for us to develop the method that we now use in epilepsy surgery and have used now since 1971. And that is the surgery can be carried out in the child that's anesthetized. We put in an electrode grid to map the seizure focus, but all the mapping and the stimulation and recording that needs to be done to identify the focus is done outside the operating room in the hospital ward. And then once that important information is obtained, the patient is brought back and the focus is excised. So this is an example of a clinical application that seems to be having some significance, which derived really out of laboratory research. So, and now, as you know, I spend most of my time really in epilepsy surgery, and especially now that I don't have some of the administrative headaches to worry about.
Well, going back, we've come forward, and then perhaps we should go backward again. Among those other figures in your life that influenced you so much, you mentioned Dr. Schwartz a moment ago. And back in the early days, if you go back to, let's drop back to 1950, around there, in your residency training period, you were associated with a number of residents who subsequently become well-known, outstanding leaders in American neurosurgery, and they came to St. Louis for some of the reasons you were there, and also because of the neurosurgical program. Do you have any comments to make about those men? And
well, those were interesting days. As you know, Bill, the people who were there at that particular time, Bob King was there, who is during this week going to be awarded the Cushing Medal, and Bill Hunt, who was the chief resident. Bob was a fellow at that time, and Bill Collins and I were both assistant residents. And Bill, as you know, has had a checkered career. He ran the program in neurosurgery at Yale, and now runs the program in surgery at Yale, and at the same time had a chance to serve as editor of the Journal of Neurosurgery. Well, it was very fast company to try to keep up with, but it was a lot of fun. And of course, at the helm was Henry Schwartz, who was a rather demanding individual, and but from which I think we all learned a great deal, and
Still do.
still do. Right. And of course, he's continued to be a very strong influence in my own career. Always been there as an advisor. Very helpful during my stint as chairman of the department. There were a number of major issues that came up for which I needed advice and counsel, and the importance of that, at least for me, can't be overestimated. Or overstated, I should say.
Well, we first met 37 years ago or so, I think it was, in the Army in Washington at Walter Reed Hospital, which were interesting days. And sort of in the midst of all this, you were the first in the public health service. Before that, went back and then had to go back in the Army.
Yeah.
Those bring up any memories?
Well, of course they do. Before getting to Walter Reed, where you and I met, I had, as a member of the Public Health Service, gone off to Thailand. In those days, we had the .4 program, Marshall Plan, and at one stage in the Marshall Plan, there was the Mutual Security Agency. I don't quite understand how that name came to be, but that's what it was called. And as part of that program, the United States sent over technical help, experts in certain fields, to Thailand, and Thailand would send over periodically some of their people to be trained here. And so I went over there with a team from Washington University. They were not all Washington University faculty. There was Paul Roseanne from Yale and a fellow named Sutton from Albany. But the rest of us were from Washington University, and we have varied specialties and disciplines. And I was very young at that time. I had not finished my neurosurgical training yet, but I went over there as the neurosurgeon, and they were interesting times, especially to be able to see the state of medicine at that time and what the problems were. I think I had told you or mentioned this before, that I had the distinction at that time of removing the first glioma over there, and just briefly tell you that we got through the operation one way or another, and I wanted that patient to do well in the worst way, and much to my discouragement and despondency, I might say, he began to run temperatures every day up to 104, and I looked at everything that I was taught to look at to try to determine the cause of the temperature, and finally in fact, the head of radiology there asked me if I thought of cerebral malaria, which of course I had not, and the patient survived, and he is allegedly said to be the first glioma that survived cranial surgery there. Whether that's true or not, I'll never know. But in any event, that trip was cut short because I wanted to do more in the way of neurosurgery, and I wanted to be more certain that what I did was going to ultimately have some influence in terms of development of neurosurgery in that country. I did play a role in sending back a young man from Thailand, but he subsequently married an American nurse and decided to stay here rather than go back to Thailand. In any event, I went back and decided to enter the Army at that time. And I was assigned first to Camp Pickett, and when Camp Pickett closed, I was assigned to Walter Reed, where I met you and Ludwig Kemp, who's a very unique and outstanding individual. I'm afraid if I start talking about Ludwig Kemp, we'll never get finished here. And what those were very important days as far as I'm concerned. One of the main reasons is that you ended up in St. Louis. And I can remember calling Dr. Schwartz and persuading him that you ought to come, and of course your decision has never been regretted by us, and I hope it's not been regretted by you.
All. Well, during all that time, or some of this time we've gone over, which sums up to the present, you, in addition to being the, before and after being the chairman of neurosurgery at Washington University, you were involved in so many organizations in American neurosurgery and neuroscience. The Journal of Neurosurgery, for many years, as editor of that, and the president of this organization, the American Association, the National Institutes of Health, and many advisory committees. Tell us some of did you enjoy those activities, and
Yeah, and
what did you glean from them?
on the whole, and in some, I'd say I did. Most of those appointments carry a good deal of work with them, as you know, but they are honors, so I wouldn't be truthful if I didn't say that I wasn't pleased to at least be considered or appointed. But at the same time, I saw many of those appointments as responsibility of individuals who were involved in organized medicine. I thoroughly enjoyed my stint at NIH when I was on the study sections and really dealt with the approval of grants. I had a later stint as a member of the advisory council. That was a little bit more politically oriented, and I didn't enjoy it quite as much as I did my days on the study section. The days on the American Board of Neurosurgery took a lot of time, but I felt that as an important responsibility because it did have to do with training and setting standards for training in American neurosurgery. And I saw that as an important role in education, as I did the editorship on the editorial board in Journal of Neurosurgery. So I found all of those to be rewarding experiences. I think I got much more out of them than they got out of me.
Wasn't it during your tenure as in one of these positions that the residency matching system was finally approved?
Well, it was. I happened to be president of the senior society at that time, but to be perfectly honest, the people who have to take credit for that are others. People like Kemp Clark, Bob King, Cone Peavyhouse, who has served after that, continues to be involved in the matching plan. But I think the matching plan has worked out very well.
Well, in 1974, when Dr. Schwartz stepped down as chairman, the Department of Neurosurgery and Neurology then combined into one department in St. Louis, and there were precedents to that, but not too many in the United States and Canada. But How do you think that's worked out, and do you think it's a good way to run things?
Well, I guess uh, the evidence that I would need to even say that it's worked out is that we're still in business. That we started this in 1974, and we still have a combined department of neurology and neurosurgery. And I think that in certain institutions, that's the way to go. I've always felt that there's a very strong intellectual thread between neurology and neurosurgery. They certainly see each other on a day-to-day basis. They have common clinical interests. They have common interests in research. There are many things that they can do better together than apart. So there are some powerful reasons for joining neurology and neurosurgery. The trick is to join them administratively, and that's where I think Bill Landau, who's been head of neurology during this time, and I were able to work out to both of our satisfaction. We spent a year before submitting the final plan for this combined department, in which we considered every paranoia and every sensitivity that either one of us might have, and at the same time trying to protect the interests of our particular specialties, but also at the same time trying to give the best assurance that the alliance would produce more than either one of us going it alone. So I think it has worked out, and many people, as you know, have said that perhaps it's worked out because we've been friends for so many years, childhood friends, went to high school together. And I'd say that doesn't have anything to do with it at all. That kind of relationship can melt very easily. I think the important factors was an integrity, an honesty, and a mutual respect, and a genuine desire for the neurosurgeon to want to see neurology get ahead and vice versa. I don't think that's the prescription necessarily for every institution. I think it varies with the institution, with the programs they have, with the people who are there. But for where it can be initiated, I think there's something to be said for it.
Well, during that period of time, I know there was this one other event, or major accomplishment for Washington University, and that was the establishment of the McDonnell Center for the Study of Higher Brain Function. Now, Mr. McDonnell, you may want to comment. I just would comment that he is at that time was the president of and developed the McDonnell Aircraft Company, which was founded in St. Louis, and he was an extraordinary man in the city and his influence in the whole community and the university. But I know that you'll tell us a little about this, but that the development of that center was, as I view it, really largely through your efforts alone. Would you agree with that?
Well, in part, yes, but I should say that without Bill Danforth, we never would have made it. Bill Danforth, as you know, is the chancellor of the university. But I did have something to do with getting that started.
What was Mr. McDonnell like?
Yeah. Well, Bill, that was a very interesting and fascinating part of my life. He was obviously a unique individual. He built McDonnell Douglas, and I think everyone knows the importance of that industry and the contributions of the McDonnell Aircraft Company. But a unique individual. One thing that isn't known about him, he had an interest in psychology, even while he was a student at Princeton. And while he was making plans and building the McDonnell Aircraft Company. He also had the notion that there was something to extrasensory perception. And he was prepared to give a large sum of money to Washington University and perhaps other institutions if they would agree to set up a department that had to do with extrasensory perception. And there was an attempt made at Washington University, but it was felt that we could not really apply modern neurobiological methods to test the hypothesis. Well, anyway, after a lull between that consideration and at a later time, Mr. McDonnell wanted to know if there was anyone at Washington University who had an interest in the surgery of epilepsy, like his friend, Dr. Wilder Penfield, who apparently was a classmate at Yale, at Princeton. And what about this new technology, the PET scanner? Was there anything to that? And Sam Guzet, who was then vice chancellor at Washington University, arranged for a sort of show and tell meeting in which I presented our experience and interest in the surgery of epilepsy, and Mike Terpagosian, who developed positron emission tomography, PET scanning, and Tom Thatch, a neurobiologist interested in the, you might say, the sequence of events that occur in the brain to initiate voluntary movement. We each presented our work, and it went successfully. And he and I finally got into a discussion about are the brain and mind separate, or are they one? It's an old argument, an old controversy. And, of course, he cited evidence that people like Penfield and Sherrington and Herrick, Eccles had all worked their entire life in studying the biology of the brain. And when they were in their twilight, they all decided that they must be separate. And I pointed out to them that that was because they were in their twilight and they hadn't fulfilled their dream, and perhaps that was their way out. But seriously, one thing that I did ask, and we agreed to, I said, let us say that I can no more prove that the mind and brain are one than you can that they're separate. But let us agree that whatever the answer to those questions are, that we need to know as much as we can about the brain. And he said, agreed. And he said, I want you to write me a proposal. It can be large or it can be small. But I want you to write me a proposal. And so the next day, I got a little slip from him, a little note, thanking us for the presentation, and he signed it yours, James S. McDonald, and yours was underlined. And I felt that there was a message in that. As you know, I then went ahead and spent several months writing a proposal, and I'll never forget the proposal was given to Mr. McDonnell to read before we had our face-to-face meeting. He was 81 years old at the time, and we met in the library of the Department of Neurology and Neurosurgery, and there was Bill Danforth, the Chancellor of Washington University, Sam Guzet, who was the Vice Chancellor, and Kenton King, who was the Dean. And I presented that proposal out loud, so to speak. And he had read that thing, and he picked up inconsistencies and typos, which I didn't think were in there. He was as alert as you can imagine. And Mike Watunsky, who was Mr. McDonnell's, you might say, chief advisor in the extracurricular activities that he had aside from his company. I have to say he picked up a few things that Mr. Watunsky hadn't. In any event, the meeting ended with him saying that, all right, we asked for $5 million, I should say, at that time, and he said that he thought it was pretty good, and he would present it to his board and see what they said. And I anticipated a long wait before their board had another meeting and so on. In any event, again, as you know, I think it was the following day or the day after, I walked into the office, and my secretary had a funny look on her face, and she had me a little pink slip, and she says, Dr. Danforth called. The McDonnell Foundation had met, had convened, and they've decided to award you that $5 million. So we had the grant, and then we were further fortunate in several years later, we were given an additional $5.5 million, and that the total of those gifts and the earnings which were achieved over the next, I'd say 7 or 8 years, with that happening, we've been able to establish that as an endowment in perpetuity for research that has to do with structure and function of the brain, psychology, cognitive neuroscience, and so on. But I count that experience of meeting this man as a rather interesting, a very important part of my career.
Well, I wanted to go from there then to your comments about your thoughts on training of young men in surgery as clinicians and scientists. Should comment, or should say that your career is, if one looks at your bibliography, has been almost totally, and with few exceptions, fundamental papers in basic science, and many times really on the cutting edge of neurophysiology, which is for a clinician unusual. You think that is still attainable or desirable?
Well, I'd put it in stronger terms than that. I think that the future of medicine, of medical discovery, the future of, you might even say, healthcare, as much as that's been maligned these days, those words, depends upon the ability of society to turn out clinician investigators. And what I mean by that are people who are clinicians who are actively involved in clinical work, who have the training and background to ask questions using modern neurobiological tools. I think if you go back and look at some of the major discoveries that have advanced neurosurgery, not just in neurosurgery, but almost in any field in medicine, you'll find that first there was a discovery in basic science that had, and at the time the discovery was made, it had nothing to do with, or it was even conceived of having anything to do with a therapeutic measure for taking care of disease or morbid conditions. It took that element, but then it also required somebody, a clinician, who was in the field who could extend those observations and apply them to the clinic. We don't have, obviously, the time to do that now, but I can cite you a half a dozen examples where that is true.
You've written about this. the thoughtful and the prepared mind, I think.
Right, right. And I think there's, I, when I wrote that, that was 5 years ago when I was president of this society, and rereading it recently, I think it still sounds all right. um, so I think that's terribly important, and I think the way that one has to go about that is that in the years of training, that for those who are interested in an academic career, they have to put aside 2 or 3 years of their life where they are trained in research, what science is all about, what is good science. They have to be prepared. And now I might say that there are problems. It's not an easy life to achieve, to be a clinician and take care of sick patients and at the same time have a substantial research program that turns out significant contributions. I think one of the things that a clinician investigator needs to do is they need to specialize. They have to limit their clinical activities. I don't see how they can be a general, let us say, a neurosurgeon, do everything that that they're confronted with, and at the same time have time for a significant research program. Now, that's not all or none. People have done that and have been able to make contributions, but it's doing it the hard way and can many times be very, very frustrating. Now, our medical colleagues can do it much better than we can. Our medical colleagues can spend 2 or 3 months on the ward, and then the rest of the time they have free to attend to their research and do it very well. And as you know, some of them have been elected to the American Academy of Arts and Sciences, and because of their contributions. But a neurosurgeon can't just stay away from surgery, for 9 months out of the year. Can't maintain his skills that way. And also a neurosurgeon, in order to teach, or a surgeon, in order to teach, needs to have they need to have their significant clinical practice. They need to have their own patients. You don't just teach at the bedside on someone else's patients, as you can do in medicine. Your classroom is the operating theater many times, and where you do a great deal of your teaching. So I think all these things, these difficulties, we've recognized them over the years, but we've been kind of passive about doing anything about them. And where they've occurred because of the will of an individual, and not because it's necessarily the thing to do. And one of the big problems facing us today is, given the individual who's been properly prepared, has had good neurosurgical training, and has made significant contributions to research, and has a bright future ahead of them, say, as a clinician investigator, and that is the funds available to do it. We're in a situation today where people who are worthy of being funded are not. The number of only 20% of the grant applications that have been approved by NINDS study section have been funded during this last year, and it's estimated only 16% will be funded the next year. Well, when that happens, you know that there are just as many people not being funded who are being funded who might be really capable of turning out better research and perhaps making more contribution. So there has to be some thought given what we're going to do about this particular kind of crisis. But I think those are there's no, I've held for a long time about what's needed in order for someone to pursue a career as a clinician investigator. And I think that there probably is general agreement about that. But I think that the institutions that are responsible for research being done, our schools, our universities, and the government are going to have to be more imaginative about how this is going to be accomplished in the next decade or so.
We come to the end of this talks, and are there any comments you want to make further about?
Well, I think one thing we've kind of glossed over or really haven't alluded to too much is that for the last 16 years I've been occupied with the department. I've been in charge of the program, and that the successful running of a program never really depends upon one individual, and your contribution to that has been extremely important, and I think for whatever credit the program may want to take or be proud of, I think that you share in that. I couldn't have made it without you. I think also one's ability to try to do 4 or 5 different things at the same time and get them all done, meet the frustrations that are encountered in running a program. The other adversities, if you're married, you better have a good spouse. And I think I mentioned to you that when Harry Truman was asked about to what he owed his longevity, or did he have any advice, he said, yep, you go out and get yourself a mother and a father that each lived to the age of 90. And I think if you go into academic medicine, I think you want to get yourself a loving and devoted and loyal spouse. And I must tell you, had Lois not been there, I couldn't have made it. So I think I'd like to end on those comments.
I think you're going to have your 10 beds in your laboratory in the future.
I have other aspirations now.